Welcome to Lecture 7 in Mathematical Foundations of Robotics, where we will keep on presenting some elementary functions. Let's start with the absolute value. Define it as follows. F of x equal to the absolute value of x is equal to x if x is larger than or equal to 0 and minus x if x is less than or equal to 0. So the graph of the absolute value is the following. Is just the identity function for x larger than or equal to 0, and it will be just a mirrored image with respect to the y-axis for x less than or equal to 0, and we clearly see that this is an even function. Another important elementary function is the exponential. Function. F of x is the exponential function with the base a and exponent x, where a is larger than 0 and it is fixed, and x instead is any real number, and this is the variable. So we are saying that the exponential function is a power with the base a, positive number, and exponent any possible real number. So examples, what can be examples of exponential functions? Well, for example, 2 to the x is an example of an exponential function. In this case, a is equal to 2, which is larger than 0, and x any real variable. Or we may have 3 to the x, or we may consider pi to the x, or we may consider 1/2 to the x, and so on and so forth. Now, you realize that from these examples, there are some of this definition that, of course, cannot be derived from the axioms on real numbers. For example, if we consider this first exponential, 2 to the x, okay? And, well, 2 to the x, if, for example, x would be equal to, I don't know, 2/3, right? So we are led to evaluate the number 2 raised to the 2/3, okay? Okay, and this is, we know that by elementary math, this would be the cubed square of 2 to the second. Okay, we can do that. But what if x is instead equal to pi? Because x can take any possible real number. So in that case, we are led to evaluate something like 2 to the pi. But 2 to the pi is not something that we know how to calculate, or at least we don't know how to do that by just relying on the axioms. So clearly, this needs a proper definition. So let's postpone the problem of giving a formal definition of the exponential, but just for the time being, let's assume just at intuitive level what could be the graphs of the exponential function, and let's split all possible situations into two cases, a larger than 1 and a between 0 and 1. Of course, we are not considering the case a equal 1, because in that case the exponential would be just 1 to the x, which is always equal to 1, so it's just a constant. Okay, so this is a trivial case. We're not considering this, so we can only consider a larger than 1, and in this case the function a to the x will be something like this, and we have a to the x, and for a between 0 and 1 instead we have this graph, okay, where this is the bisector. As expected, the two graphs are in the first and second quadrant because, of course, the power of a positive number can only be a positive number. Right, so let's now try to identify some features of these graphs, okay? And without loss of generality, let's consider a larger than 1, okay? I'm saying this because, of course, all the considerations that I'm gonna do can be easily extended to the other situation, okay? So f of x equal to a to the x is a function, is of the type f from r to 0 plus infinity. In fact, the function never attains the 0 value, but it will tend to that, okay? But it is also a strictly increasing function. In fact, we see that this function is always increasing, which is also something that we can understand, because if we have a positive base larger than 1, the larger the x, the larger the exponent, the larger the power. Also, we can say that this function is, so if this function is strictly increasing, that implies that this function is injective. But by just looking at the graph of the function, we see that every possible positive real number on the y-axis is hit by the function. So we can also say that this function is surjective. Well, but that implies that function is invertible. So let me call the inverse function, the inverse function is g, that now goes from 0 plus infinity to r, and let me call this function g of x equal to the log base a of x, and this is again the definition of the logarithm. If we want to build the graph of the logarithm, we can rely on the theorem of the graph of the inverse function. So let me first consider the case where a is larger than 1. We know that this was the graph of a to the x, and if we do the mirror image with respect to the bisector, remember that this was 1. Well, the mirror with respect to the bisector will be this, and so this will be log base a of x in the case where a is larger than 1. Let me consider now the other situation where the a was in between 0 and 1. We had that the graph of a to the x was this one. Okay, and if we now build the mirror image with respect to the bisector, what we get is this. Which of course will tend to the bisector between the second and fourth quadrant. So this will be the log base a of x in the case where a is in between 0 and 1. Okay, so we have now a full definition of the logarithm for as an inverse function of the exponential. It's time now to go back to the problem that we have mentioned at the start. So let's try to see what could be a formal definition of the exponential function. So we mentioned this problem that for example 2 to the third can be understood from the algebraic axioms of real numbers as well. 2 to the third is just 2 times 2 times 2, and we know that the product is something that was defined in the axioms. But how about 2 to the pi? Well, this is clearly a problem. Now, it can be proved that for every real number a larger than 0, there exists a unique function fa that goes from r to 0 plus infinity, such that the following conditions are verified. Okay, so first condition should be that fa of x plus y is equal to fa of x times fa of y. You see, I'm just giving a first condition that needs to be satisfied. I know that finally this f of a function will be the exponential, but still I don't know that, so I'm using just this fa as a symbol, as a generic symbol of a function with a as a parameter, and I'm just listing down a few conditions that this new function needs to verify. And clearly, because this is one of the properties of the exponential, I'm enforcing this property to be as a constraint for this new function. Second would be that fa of 1 should be equal to a. Now, let's suppose that we stop here. We can prove that if we only rely on these two, there exists a unique function f of a, fa, which however is defined just on the rational numbers and will satisfy these two conditions. So there would be, if we just restrict ourselves to the rational numbers, at this point these two conditions would only define only one exponential function that would do this. However, there are infinitely many, but there are infinitely many fa defined on the real line 0 plus infinity which satisfy 1 and 2. So for that reason we need to add another condition. So this third condition can be taken among three options. So we'll have three options for this third condition. So first option would be that fa is continuous. And you see that fa defined on the rational numbers doesn't need to be continuous function, right? Or certainly we know that that is not going to be continuous. But if we now enforce that this function fa has to be continuous, there will be only one possible choice, which turns out to be exactly the exponential. Now this is, let's say, a weak condition, but we can also go for a weaker condition. So we can ask that fa is monotonic. In fact, we know that if a is larger than 1, fa, the exponential, will be strictly increasing. If a is in between 0 and 1, fa is strictly decreasing, so in any case we would have a monotonic function. There is also the weakest possible, this is the weakest possible condition that we can enforce, which is the following, which is the fact that there exists a rectangle in the first union second quadrants which does not contain points of f of a. So what I'm saying is that we know that the function has a graph that is contained in the first and second quadrant. If we manage to find a rectangle, it can be also very small, such that does not contain any points of f of a, well, it turns out that the only possible choice would be exactly the exponential with the graphs that we have introduced before. Right, so we can conclude this saying that it can be verified that the only function that satisfies 1, 2, and one of the possible three options for the three condition is the function given above with those graphs. Now the problem still remains, for example, how can we evaluate a number like 2 to the pi? We don't have an operative procedure for doing this. So far we have proved that there will be only one function that satisfies all these conditions, which is good. So this is a formal definition, but we still miss an operative definition. But this is easily done because we can just consider the supremum of this set, the set which is generated by evaluating 2 to the q, okay, where q is a rational number and q is less than pi. So we build a sequence 2 to the q for every possible rational number less than pi, and we take the supremum. So this is what gives the definition of 2 to the pi. Okay, at this point we have quite a rich list of elementary functions, but we can build a new function by just applying very simple operations on their graph. So next topic will be operations on graphs. So let us given the graph of f of x. Okay, so first operation, if we do f of x plus a, okay, this will produce a vertical shift of the graph, and this graph will move upward if a is larger than 0. Just a shifting upward or downward depending on the sign of a. If instead we want to make a horizontal shift, we can obtain that by just replacing x with x plus a. So let me show you an example of this. Okay, let's suppose that we have this function, which we know very well is just x squared, and of course we know that if this is f of x equal x to the square, we know that f of 0 is equal to 0. And let's suppose that we want to shift this to the left. So we want to produce this graph which is shifted to -1. So we are moving 1 to the left. Well, this can be simply obtained by just replacing x with x plus 1. In fact, this would be x plus 1 to the square, and we know that this x plus 1 to the square is equal to 0 when x is equal to -1. So we have now a horizontal shift of the function to the left by just replacing x with x plus 1. Good. Another easy operation that we can do on the graph is the mirror with respect to the x axis, and this can be obtained by just doing minus f of x. If instead we want to do the mirror with respect to the y axis, well, this is obtained by doing f of minus x. And if we want to do a mirror with respect to the origin, then we have minus f of minus x, which is basically the composition of two mirrors, one with respect to the x and one with respect to the y. If we replace x with f of the absolute value of x, or sorry, let me start with the absolute value. First, let's do the absolute value of x. Okay, so this will just mirror the negative parts of the graph. And if finally we can consider f of the absolute value of x, well, what this operation will do is that basically the graph with x less than or equal to 0, which is the only part that will change, right? Because for x larger than or equal to 0, nothing changes. But for negative x, it happens that the graph with x less than or equal to 0 disappears, and it is replaced by the graph with x larger than or equal to 0 mirrored with respect to the y. Okay, so let's do an example just to make sure that these elementary operations on graphs are clear. Okay, so let's do this example. Let's consider now the function f of x equal to the absolute value of x to the square minus 3. Okay, so we'll start with the usual function, which is x to the square, right? So this is x to the square. Now we know that the first thing we need to do is basically a vertical shift downward of 3. So we want to move basically in this position, where this is minus 3, right? So the effect of this first shift x squared minus 3 would be that the new function, this is x to the square minus 3. This is x to the square minus 3. Okay? And what will be this point and this point? Where this is where x to the square minus 3 is equal to 0. So this is clearly square root of 3, and this is minus square root of 3. Good. And this is minus 3. Now we need to apply the absolute value. We said that applying the absolute value means that basically all the negative parts of the graph will be mirrored with respect to the x. So what we need to do is basically taking this, the negative part, which is this part here, and mirror this with respect to the x-axis. So what we get is something like this. So the final graph of x to the square minus 3 in absolute value will be the following. So this will be x to the square minus 3 in absolute value, with this being minus square root of 3, square root of 3, and 3. Okay, so now an important observation is that if f is injective, what will be the graph of this function like? Well, every line which is parallel to the x-axis crosses the graph in at most one point. It might not cross the graph at all, but if it crosses, it will do this only once. If f is surjective, every line parallel to x crosses the graph in one or more points. So of course, if there exists, let me give an example of this, okay? If we have a function like this, for example, you remember that this is x to the cube, right? So in this case, for every possible horizontal line that you can pick, every possible horizontal line parallel to the x-axis, we have at least one point that crosses the graph. Not only that, we also have that every parallel line will cross the graph at most in one point. So this is clearly an invertible function. If we had instead a graph like the absolute value, well, this function is neither surjective nor injective. It is not injective because if I pick, for example, this line, we see that this line is crossing the graph in two different points, so we cannot have injectivity. Even if you see that, of course, for this horizontal line we don't have any crossing. That might not be a problem for injectivity, but this is the problem for injectivity, the fact that the parallel line will crosses the graph in 2 points. It is not surjective as well because there exist lines like this one that do not cross the graph at all. So that is just a visual way of checking the injectivity. Now, in the last part of this lecture, what I want to do is just to make a connection between equations and injectivity. And this is just to highlight the importance of injectivity when solving equations. For example, let's consider the following exponential equation. 2 to the 5x plus 4 equal to 2 to the 7x plus 2. Okay, how do we solve an equation like this? Well, usually we'll do this. We'll say, okay, if the left hand side has to be equal to the right hand side, that means that 5x plus 4 is equal to 7x plus 2. And then, of course, we solve this very simple equation. However, this relies on the fact it is hidden in our process that we are assuming that f of 5x plus 4, where f is the exponential with power 2, is equal to the f of 7x plus 2. Okay, so of course from this will follow, right, that 5x plus 4 is equal to 7x plus 2. Now this implication is relying on the fact that this is true if and only if f of x is injective. In fact, I will remind you now the characterization of injectivity. We saw that basically when f of a1 would be equal to f of a2 if the function is injective, from this follows that a1 is equal to a2. So we are heavily relying on injectivity when solving an exponential equation like that. Now, the same way, if we have a logarithmic equation like logarithm base 5 of 5x minus 4 equal to logarithm base 5 of 7x minus 2, okay, so Well, in this case, remember that what the logarithm function for with base 5 look like, it will be something like this. Because in this case, so this would be logarithm base 5 of x, because remember that 5 is larger than 1. Okay, so this would be, and we know that this is clearly an injective function as it is always increasing. So when we want to solve this equation, well, we actually need to check, well, to solve the equation in this way. We say that 5x minus 4 is equal to 7x minus 2 as long as 5x minus 4 and 7x minus 2 are both larger than 0, because this is the only possibility that the logarithm is defined. Okay, so this would be important to check. Now, there is also a relation between injectivity and inequalities. So let me say inequalities and injectivity. Let me just do a few more consideration on this. And again, let's consider an equality like f of 5x minus 4 larger than or equal f of 7x minus 2. Okay? Now, we can, from this, we can basically deduce that 5x minus 4 is larger than or equal 7x minus 2. This can be done, let me put this in red, if and only if we know that f is strictly increasing. Right? So, in other words, from the initial inequality, we can eliminate f and just work on the arguments of f only if we know that f is strictly increasing. In fact, I mean, just reminding to ourselves what is the definition of a strictly increasing function. We know that if f of a is larger than or equal f of b for a strictly increasing function, that implies that a is larger than or equal to b. Okay? So, but we can only do this if f is strictly increasing. That wouldn't work if f would be weakly increasing. Okay? So, what we can do is that basically if we know instead that f of a, if we have an inequality like this, f of a larger than f of b, well, that would imply that a is larger than b, and in this case we can only say that this is true if f is weakly increasing. So in this case, this condition of being weakly increasing is enough to get rid of the f function. But this holds only for strict inequalities like this. Okay? Now, let me prove this first thing. I want to prove this first. Okay, let me do something. Let me move this second inequality down, and I just want to give a proof of this. So I just want to give the proof that the inequality on the f implies the inequality on the arguments if and only if f is strictly increasing. Okay, let me give the proof of this. Well, let's assume, right? Let's assume that let's assume by contradiction, basically, by contradiction, that A would be less than B. Now, if F is strictly increasing, then it would follow what? Well, from A less than B, it would follow that F of A would be less than F of B. But this is clearly a reduction ad absurdum, in the sense that we have assumed right at the start that f of a is larger than or equal to f of b. And now, by just contradicting the fact that the a is larger than or equal to b, we came up with the conclusion that f of a is less than f of b. So this is not possible. Cannot be the case. So the only possibility is that a is larger than or equal to b. In a similar fashion, you can prove basically the other inequality with the only the strict inequality. Okay, a final consideration on the image and pre-image of sets. Okay, so let's consider, for example, f that goes from R to R, and let's take the usual f of x equal to the x squared. Okay, but we just want to find the image of the interval -1, 2. Okay, so we want to find this the image of this. So I'm just reminding you what we have. This is the x-axis, so we have -1 here, we have 2 here, and we know that the f of x, x squared, has this graph, right? So what we would like to find is basically the image of this interval on the y-axis. Right? So how can we proceed at doing this? Well, the way is the procedure for to find the image is the following. So first, identify -1, 2 on the x-axis, which we have just done, right? So this would be just the interval -1, 2 on the x-axis. Then, next step is identifying the corresponding part on the graph. And what is the corresponding part of the graph? Well, this is the part that corresponds to the chosen interval. And now, as a final step, we need to project on the y-axis. So if we do now the projection on the y-axis of this, what we get is exactly this. So finally, we can say that the image of -1, 2 is the interval 0, 4. A similar process can be applied to the pre-image. Okay, so let's say that we would like to find now the f to the minus 1, because the function is invertible on the first quadrant, f minus 1 of the interval minus 1, 2. Okay, so once again we are in this situation where we have the graph of x to the square but now we are looking at something that the pre-image of minus 1, 2. So we are looking basically at minus 1, 2 here on the y-axis. So what will be the first step? Well, identify, very similar to that, identify minus 1, 2 on the y-axis. And this is now done, because this is minus 1, 2 on the y-axis. Then we would identify the corresponding part on the graph, and the corresponding part of the graph would be you see just this one. And finally, project on the x-axis. And the result of the projection would be this. But of course, something strange happened. And this would be something, I don't know why this is happening, between square root of 2 and minus square root of 2. Right? So we can clearly say now that the counter image would be simply minus square root of 2 square root of 2.